We're going to start with the basics of carbon, then meet our first family of molecules, the alkanes, and see how they all fit together. After that, we'll kick it up a notch with alkenes, and then we'll get to the really cool part, the special attachments that give molecules their unique powers.
All right, section 1. Let's start at the very beginning. When you hear organic chemistry, all it really means is the study of stuff made with carbon. And to get a handle on the massive things carbon can build, we have to start with the absolute simplest combo possible. And it does not get any simpler than hydrocarbons. You know, the name kind of gives it away, right? These are molecules made of only hydrogen and carbon atoms. That's it. Natural gas, propane, gasoline, those are all just different hydrocarbons. They're the first, most basic family in the whole organic chemistry playbook. And this slide nails that only rule perfectly. On the left, you've got butane. See? Just a chain of carbons loaded up with hydrogens. It's a pure hydrocarbon. But look at the right. That's butanol. It looks almost the same, but see that one little oxygen atom in that OH group? That changes everything. It's not a hydrocarbon anymore. That one atom makes all the difference. Okay, so now we know what a hydrocarbon is. Let's meet the simplest family inside that group, the alkanes. Seriously, these are the workhorses, the absolute bedrock of organic chemistry. Everything else is kind of built on top of these. This right here, this is a huge deal. This shows you exactly what makes an alkane an alkane. On the left, we have ethane. Notice it only has single bonds between the carbons. We call this saturated because it's holding every single hydrogen atom it possibly can. It's full. Now, that single bond also lets the molecule twist and rotate freely. But look at ethene on the right. That double bond makes it unsaturated, and it completely locks the molecule in place. It's rigid. There's no twisting around that bond.
So let's lock in that definition. An alkane is a saturated hydrocarbon. And that word saturated is so important. Just picture a sponge that's been completely soaked in water. It can't hold another drop. That's an alkane. Its carbon chain is totally soaked with as many hydrogens as it can possibly hold, all thanks to those single bonds.
Okay, so there are literally millions of organic compounds out there. How in the world do chemists keep them all straight? Well, they group them into families, which brings us to this really beautiful logical idea called the homologous series. A homologous series, it's just a fancy term for a family of compounds that all follow the same rules and have the same general formula. I like to think of them as siblings. You know, as they get bigger, they look a little different, but they all share the same family traits and behave in really predictable ways. Let's actually build the first few members of this alkane family. Think of it like a ladder. We start with one carbon, methane. That prefix, meth, just means one. Now add another carbon, and we get ethane. F means two. You see the pattern? 3 carbons is propane, and 4 is butane. For every step we take down this ladder, all we're doing is adding 1 carbon and 2 hydrogens, a little CH2 unit. It's that simple.
And because this pattern is so perfect, we get this awesome cheat code for the entire alkane family, CnH2n plus 2. So what does that mean? It means if you tell me the number of carbons, which we'll call N, I can tell you exactly how many hydrogens there will be. Let's test it out on propane. N is 3, right? So 2 times 3 is 6, plus 2 is 8. And what do we have? C3H8. It works. It's a super powerful shortcut. Okay, we've totally mastered single bonds. Time to level up. Now we're going to see what happens when we throw in that rigid carbon-carbon double bond, which creates a whole new family called the alkenes. All right, so here's our new rule. An alkene is an unsaturated hydrocarbon, and that word, unsaturated, tells us everything. It means it's not holding the maximum number of hydrogens. And why not? Because of its defining feature, that carbon-carbon double bond. That double bond is the center of all the action. It's what we call a functional group, and it's what makes these molecules so much more reactive.
So let's look at one. This is propene. The name tells you what you need to know. Prop means it's a 3-carbon chain, and that ene ending screams, hey, there's a double bond in here. And remember how that double bond is rigid? Look what it does to the shape of the molecule. It forces all those atoms around it to lie flat in a single plane. Now, when the chain gets longer, like this 4-carbon butene, we have a new problem. We have to say where the double bond is. This molecule is called but1-ene because the double bond starts on the very first carbon. If we moved it to the middle, it would be but2-ene, and that's a completely different molecule, so that number becomes a crucial part of its identity.
So far, we've only been playing with carbon and hydrogen. But honestly, that's where the real magic of organic chemistry begins, when we start swapping out a hydrogen for something more exciting. This brings us to our last and maybe most important topic, functional groups. So what is a functional group? It's the most important part of the molecule. It's the specific atom or group of atoms that gives the entire molecule its chemical personality. Here's a great way to think about it. If the carbon chain is the skeleton, the functional group is the part that actually interacts with the world.
Let's watch this happen. We'll start with our plain 2-carbon ethane skeleton. Now watch, we'll just swap one of those hydrogens for a chlorine atom. Boom, we just made chloroethane. Okay, let's try another one. Swap a hydrogen for this OH group, and suddenly we have ethanol. Yep, that's the alcohol in beer and wine. One more, let's add this COOH group. Now it's ethanoic acid, the compound that makes vinegar taste so sharp. See? Same carbon skeleton, but each new group gives it a completely new identity.
So, let's put it all together. We started with the simple saturated alkanes with all their single bonds. Then we introduced a double bond and created the more reactive, unsaturated alkanes. And from there, the real fun started. By swapping out just one hydrogen for new groups of atoms, we unlocked completely new types of molecules with new personalities, like alcohols and carboxylic acids. It's amazing how you can build so much variety from such a simple set of rules.
And that's where I want to leave you. Just think about this for a second. We've only scratched the surface with simple chains and a few functional groups. What happens when you start combining them? What if you put an alcohol group and an acid group on the very same molecule? What happens when the chains bend back on themselves to form rings? The possibilities are, quite literally, almost infinite.